Okay, so the title of the talk is Human Norms for Robots, Representation, Reasoning, and Learning. And this is basically my topic in my research. So let's start. So I will say something about motivation, then I will go deeper about exactly what are the problem statements. I will represent the formal framework that I use for addressing these problems and research questions. Once we have a framework, we can identify computational problems that are related to norms. I will say something about verification and planning. My favorite topic is abstract learning, and then I will just say something at the end about the summary. So about motivation is basically that we as humans, we almost always using these social norms when interacting with each other. Basically, in our society, our behavior is guided by social norms. On the other hand, robots are increasingly becoming more and more part of human societies. And therefore, it's essential that robots can be social aware. And this simply means that they can understand, reason about, and learn from human norms. This should bring certain benefits, like only from the human perspective. It should bring about like smooth human-robot cooperation and interaction, but also from technological or computational perspective, norms can help robots and algorithms that governs them to simplify decision making, because there are already prescribed behavior in the norms that a robot can use. They also facilitate cooperation, decrease communication, because in a certain situation, the more you're aware of it and the more you're aware of the norms and things that you should do in a certain situation, this lowers the need for communication. There is also scientific and cognitive perspective, where a lot of people believe that investigating and making robots social may bring us a step further to our understanding human style or human level AI. Okay, so more concretely on exact problem statement that I'm addressing. And this problem statement consists of three main parts. First part is how to represent norms. And then when we have this representation with these certain characteristics, how to reason about norms and how to learn from social norms, and what are the problems related to learning, how we can address them also with reasoning. So for the representation, there is this problem of that it's usually hard to specify a norm that is both understandable by human and the robot, because human norms are usually encoded in human language, and on this level of abstraction, robot cannot understand and know what to do exactly. On the other side, if we specify norm on a level of robot trajectories and states that robot sees, basically it would require mathematical precision and complexity that it would be very hard for humans to understand. So this is one problem, one research question that I'm addressing. Then also it's important to encapsulate norms within a certain social context, in which they are true, because it's possible that there are different situations, but in different environments, and we would like to bring norms in the social context, yes, to bring them together. Then also it's important that norms can can represent different things. For example, they should represent obligations, like for example that a robot is he have to do something or it's forbidden to do something, but also norms should specify temporal constraints. For example, that some action should have to be done before other action or in the same time and the other action is done. And also this includes a representation of spatial norms and spatial requirements, because maybe we want to say to a robot that something should be done only in the certain location and stuff like this. So this is one of the requirements. And maybe the most important thing here is that norms are reusable. So we can, because norms don't depend on particular concrete execution, but on a little bit abstracted level of a situation and in the social context. So we want, if we recognize the same situation in another domain, in another environment, we should be able to reapply and reuse already defined norms. And then, yes, and then the questions about reasoning about these norms and learning from the social norms. One of the most important problems is if we have robot execution, and can we say that this execution formally verify that this execution adhere to norms or not? And this is one of the basic problems from which planning and learning later can be addressed. Okay, so as I said, there is this problem of norms where they could be too abstract or they could be too specific for robots. And multi-agent system is an area that is investigating norms, and there are norms on a different level of abstraction. But the problem is that in abstract norms, it's really hard to connect these abstract norms to physical execution on which robot operates. So basically, it's hard to apply to robots. On the other hand, in robotics, we have norms that are usually specified on a very low level, on a level of trajectory and states that robot perceive. And then the problem is it's very hard to take the same norm and reuse it in another situation. And one of the important points that I'm addressing is bridging the gap between this abstraction in mass and robotics. Okay, to do that, I'm using the term institutions. In multi-agent systems, institutions is defined as a set of norms. And basically, I'm encapsulating the social context by using the term institution. But one of the problems with the term institution, it stems from social sciences and economic sciences. It's adapted in multi-agent systems where institutions have a very simple definition. It's just a set of norms. It doesn't matter on which level of abstraction they are. But generally, the ambiguity of this term is high. For example, some may say that the institutions are the rules of the gaming society, or as Ostrom saying, they're prescriptions that humans use to organize all forms of repetitive and structured interaction, and it means on all levels of interaction, which is basically what I'm doing later. Then they can be seen also the part as an action structure, or they could be seen as modification made to the environment or to the internal mechanism of the agents that interact. One of the interesting definitions is that institutions may be as cognitive frames or shared set of meanings with which humans interpret the behavior of ourselves or others. And I know I like this definition when I'm thinking about institution and learning, as you will see later. Okay, and I said in computer science, it's simply defined as a set of norms. So, okay, so let's switch to my framework and representation. So here you can see two domains. Basically, in the first domain, there are two concrete agents, and they are passing and giving some concrete objects. Similarly, in the second domain, we can also see two agents, and they're also passing and receiving other kind of objects. This can be formalized very simply, basically, as a tuple of agents, behaviors, and objects. And I'm providing here an illustration how this look like. And these elements here, they are connected with affordances. This simply means that if the object is, let's say, a chair, so chair affords sitting to some agent, probably human agents and not robotic agents. We could also say that apple affords eating to certain agents, but not to others. So this affordance is basically a triple saying which object can be used with which behavior by what agent. Okay, so going back here, this is the physical domain. But as humans, and as point out by many different authors, especially Searle, as humans, we build this social space or institutional space where we can see both of these domains as the same as the abstraction, basically the same thing. Both domains are instance of the same trading institution or selling buying institution, let's call it like this. And this institution is characterized by the roles of seller, that there is a role of buyer. There are also goods that the seller wants to exchange. And there is a paying form here, and there are actions that have meaning in this institution, like selling and paying. Okay, so this can also be represented very simply. So let's say there are roles that define institutional or this context where the thing happens. There are the social actions, simply acts, and there are artifacts. And artifacts are these objects that have meaning for the interaction in the institution. For example, cash can be such object. Okay, so connections here are actually high-level norms, because then we can say, must buyer pay seller? So buyer is a role, some role, and basically what this says is the buyer must pay to a seller. Seller is another role, and pay is this high-level action. We can also say, on this level, it's easy to specify temporal norms where we can say, like customer pays money before waiter serves food, for example. And this is still abstract, and robot wouldn't know, or computational agent, artificial agent wouldn't know how to use this, basically. But it's easily understandable by humans. So this is abstraction of the institution or social context. And okay, and continue forward. Now, these two things have to be connected. And these connections we call grounding. So basically, we can say that this category, this seller here, is grounded to a particular agent. The goods are grounded to a particular object that we want to exchange. Paying form here is cash. buyer is this another agent in the physical domain here. So, and paying is this action of giving the paying form, whatever it is. So paying form here is cash, and paying form here is credit card, for example. This is not grounded. So now this abstraction, this abstract knowledge is grounded to this particular concrete physical domain. Okay. So basically now, in this example, we have this trading institution with buyers, with sellers, with actions that have this social meaning, and artifacts that have this meaning, social meaning of this particular interaction. And we have physical world that can have many agents, can have many behaviors and many objects. Okay, so here how grounding looks like, how it's connected. And we call it grounding. Sometimes it's called also social grounding to make a difference from simple grounding. It's called also anchoring in robotics, semantics mapping, and in multi-agent systems, it's sometimes called count as, because you can, let's say, you can say battery count as goods in this context, in this institution, or giving count as paying in this context, Sally count as seller, and so on. Okay. So final thing to represent a physical world. So now we have just symbols like agents, behaviors, and objects, but they should be described. This domain should have states to be described, basically. And this state could be, for example, a color of an object, or attribute saying is behavior giving activated on agent Robbie. So Robbie is the name of the agent. For example, distance between two agents, Robbie and Sally, and yeah, they have the general form of attribute that describes the relation between these entities inside domain. So yes, and okay, the important thing to say is that until now the things were static. So I will just represent a picture of a physical domain, but actually the domain and state variables that describe this domain, they evolve over time. And this evolution of states there is captured by trajectory. And trajectory simply maps time to state, to states. So at each time point, we can take the states of the domain. Okay, so here it's also important that once we have trajectory, and that trajectory is a level on which robot operates. It basically depends on these attributes. We can define norm semantics. And norm semantics would be most simply said, let's say, most semantics are conditions over a trajectory. And then if this condition is satisfied, the norm is fulfilled, for example. If it's not satisfied, it's violated. Okay, it's a little bit more complex than that, but this, I think, is easier for understanding. This is the condition. Okay, if all the norms in an institution adhere, if trajectory adhere to all the norms in institution, then we say the trajectory also adhere to the institution. Okay. So once we have this framework that abstract this abstract from the physical layer, that describe trajectories and norm semantics, we can start identifying what is important to calculate inside this framework. And here I provide this table where we have norms, a set of norms, which is also institution. When we have grounding, trajectory, domain, and semantics. So those are the parts of a representation. of the framework. And depending what is given, what is already provided, we can define the different problems. So the basic case is when everything is given. So we have norm specifications, high-level specification. Also, we have norm semantics. If you remember, the condition on the trajectory, conditions on trajectories. Trajectory is provided. So we already have this execution that happened, and we have grounding. We know which abstract element correspond to particular physical detail. So when we have all of this, the problem is to verify, does this trajectory adhere to provided norms? And that's it, just to check if trajectory adhere to norms. Then other relevant problem is if trajectory, for example, is not given. Let's assume that this is given, for example. So if trajectory is not given, we want to be able to plan, to create such a plan that when executed on a robot, it will produce adherent trajectory. So trajectory that adheres to norms. Basically, this problem is a little bit more complex if the grounding is not given. So then we have to plan which robots or which objects should be used. And this is also very similar to learning. We should, for example, learn a policy that generates execution, that generate actions that will lead to trajectories that adhere to norms. There are also other problems, like, for example, grounding problem. Grounding problem is basically everything is given, the trajectory is irrelevant, but then to figure out which abstract parts to connect to which physical parts. Then interpretation problem is interesting also, because it's similar as grounding, but the trajectory is given. So additional conclusion can be done from trajectory. Example from this would be that we know that the bunch of children are playing football, but they're playing football, let's say, on a meadow, and they're using trees as posts, goal posts. So basically here we have our institution, and we need to figure out that the concrete tree in a physical domain is actually what is grounded to the goal post, and that the meadow is grounded to a football terrain, basically making this association, and so on and so on. Interesting problem is also relational learning. When we have these abstract norms for humans that humans understand, we have all other things, but we don't have semantics. And basically we have to learn what it means to be in some institution, for example. Basically learning semantics of the norms. Okay, but here I will focus mostly on verification and planning. And before doing verification, before starting this, let's just address what and how questions, because everything that I was speaking about until now is what questions. So we have norms and their semantics, and they basically specify what should be done in different situations. So they list these norms, and norms said you are obligated to do that, or you're forbidden to do this, and you should be there before something else, and so on. But the question remains how an agent should achieve what's specified here by declarative norms. And to answer how questions is where we use planning and learning. Okay, so first let's start from verification. So here we have some story, let's say a short story. And there are two agents, Sally and Robbie. One is human, other is robot, and they are exchanging some objects. Now the question is, is this a trading story? Verification process should be able to answer this question. Also, we have another story where everything is the same except the last state, when Sally is basically returning the cash that was given by Robbie previously. So she doesn't give a battery, but returning the cash. So what about this? Is this a trading story or not? And we are solving verification problem by taking what we have: norms, domain, grounding, and semantics. We assume that this is given to if you remember from the table, and then reduce this problem to constraint satisfaction problem. This is already known problem. So for those who are not familiar with the constraint satisfaction problem, this is maybe the easiest constraint network that I could think of. For example, there are two variables and they can have different values. Let's say that this has value 3. There is a constraint that 3 should be smaller than whatever is in this variable. And then the goal of a solver is to find assignment, basically find values so that constraint is satisfied. So for example, answer 1 would fail because 3 is not smaller than 1, but 5 would be okay because it is larger than 3. And basically, I mean, this is basic of what constraints, what it is. And we are using this technique by representing our states as variables in constraint network. So we can, for example, represent that activation of behavior on agent and its value. I'm saying we can put value here because we already have a trajectory. So we can fill in all the values of all the states. And we can build this constraint network. Okay, the next slide, where the norms are constraints. So it looks complex, but it's really simple because so we have all the values in these variables, and only thing that we have to do is to basically check if this constraint is satisfied or not. If all constraints are satisfied, then the trajectory adheres to institution. And yeah, so here is basically this abstract norm, and here's the norm semantics that is checked. Grounding also play a role because from grounding we are choosing particular agents that are buyers and particular actions and so on. But maybe not lose more time here. So basically this is the mechanism that can help help us to solve the verification problem. And then concretely in this case, we have certain states that can be checked and turned into this network. I don't think I should go into details here, but basically these states, they go to constraint network, and then semantics is constraint that is checked. So basically, I think you have to believe me here that this is adherent execution. But for example, when Sally is returning the money, the cash, we have certain states done that, and then when checking, for example, this norm here, that the seller should give goods. The problem is that goods are grounded to a battery. And here we will have a battery, but what actually happening is a cache. So it won't hold here and it will fail. And in this way, we can check if a norm is satisfied or not in the whole institution. Okay, now I'm moving to this planning section. And verification can be used for planning basically, so we have a robot domain knowledge because this knowledge is, let's say there are operators that the robot knows how to use to make a plan. And robot makes it plans, but these plans go to this verification module that is taking the norms, the grounding and semantics, and then answering, okay, but your plan is adherent, fine, then go further, or your plan is not adherent, so please replan, or so for the next evaluation of the trajectory that is created, plan that is created. However, this is useful, maybe more useful for learning approaches, because when we have this robot domain knowledge and we have a planning language, we can use this institution specification and create operators and directly into the planner domain. And this is approach that I'm using basically. And furthermore, since I'm using a planner that is based on constraint network and solving it, I can add the variables that has to be fulfilled basically directly into this network, but I will not go into details. So, okay, so with this, we did various experiments. So we were able to encode rules for the game that was played between a robot and a child, my child here. And we could change a human participant with another robot and it would still work. We also designed an experiment with guidance and escort, because this robot is escorting the students to see the lab. And then in the lab, there is another robot that is explaining what are different parts of the lab. Maybe I can find the video to show you. And this is done also with cooperation with the student from APFL in Switzerland and IST in Portugal. So basically there are two robots here in front and the back, and they are guiding students to the laboratory. Okay, maybe I can get it a little bit faster. So they're now escorted here in the laboratory. A robot is explaining about lab and going to different points. And the trick here is that you can change robots, and you can also change points where the robot goes simply by changing grounding. So it includes this experiment includes 3 robots. One is that staying behind the students. This robot is one that can speak actually. So it's a Pepper robot. So it explains the different points where the students are taken. Basically, that's what. And we made like 60 trials with students. Maybe more important is this video where you can exactly see how verification works. Basically, okay, I will go. So here the scenario where 2 humans are grounded to a buyer and to a seller. Now, seller is giving the payment, and the blue sponge is a payment form, and then the buyer is giving sorry. Okay, maybe I should start this over. But basically, it's if I return a little bit, it's the buyer is paying. So yellow sponge is paying form. The buyer is paying after it received goods. And one of the norms in this institution is that buyer must pay before it received goods. So the framework can capture this and say, okay, but this temporal norm is not satisfied in this case. Okay, so the next. Okay, so now the buyer is first paying, and the yellow sponge is a paying paying form. And then the seller is giving goods. The pepper here, he captures the state of the environment and what's happening, and then sends to a computer that is basically running this constraint satisfaction problem, solving verification problem. And in this case, everything went according to norms. So all is fine here. We could also ground this scenario to a robot and a human. And it's interesting because then the robot has to cooperate with the human. And part of computation is calculating human states and human adherence to norms. Another part is planning robot behavior. So buyer is giving the payment here, and then the human will give the goods, which is a black box when the robot is ready. And it's really slow. I speed it up 8 times. In the final scenario, we can ground this abstract institution to 2 robots, and they will plan to produce this adherent trajectory, exchanging item, paying and giving goods, basically. Okay, so yes, okay, now seller is giving the goods. Okay, so let's move to another section, which is about abstract learning. And here, let's say we have a similar problem, example problem. Let's say that there is a robot Robbie that is in a hardware store, and it has a goal to get the desired item. And the Robbie, it can move 1 step forward and backwards. It can rotate 1 degree left and right. It can pick objects, which is atomic action, or do the money transfer. And in this environment, in this physical domain, basically we have a door, we have a cash register, and these different items. Okay, usually what we want to do, so to get the desired item is a problem that could be solved with basically normal reinforcement learning. And then the robot will just take the item. What we want here is, and that's something known how to do. What is not, what is unknown, and what this is addressing, what my research is addressing, how to include norms so that, okay, we want the desired item, but we also want to respect the norm in the institution. Like, okay, get the item, but then pay at the cash register. So you have to be here to pay. You should also get goods before paying. So first get the goods and then come here to pay. Okay. So normal reinforcement learning is, this is a famous schema that reinforcement learning agent is producing actions. These actions are changing the environment and the states in the environment, and then the agent receive state, the new states, or state in the next time step, and then it take this state to produce the action. From the environment, we also have a reward, and when agent receive these rewards, and it use it to learn what's the best set of actions, so that rewards, these gains are maximized. Rewards for the environment are maximized. And this is normal approach. So here, what I do in my research is basically adding this institutional model, this social context, and it provides 2 things in reinforcement learning, and that's prior social knowledge, so that's coming from norms, and abstraction. And let's first see what about prior source of knowledge. So we have norms, and now if you remember from previous slides, the norm can be fulfilled, can be violated, or can be neutral. And we can use this information to create a reward function. And this simply means, let's say, if agents start fulfill the norm, then they will receive reward. If they break the norm, they may receive negative reward, or right. If they don't do anything, there will be no reward. So basically, we can specify this function and decide how to manage these rewards. The important thing here is that agents learn concrete behavior while following these abstract norms given in the institutional model. That's an important thing. The other important thing is abstraction of these states. So as we saw, the agents, they learn from the rewards and states as it comes from the environment. So basically all the states that come from the environment, and there are many states that are not important for the task that agents wants to solve. And let's see if there is a way to take what is important and abstract this, and let's see how it works. But to do that, I will have to go through a representation for machine learning. And basically, I don't think I have time to do this, but basically a domain, it can be the states of the domain, it can be represented as a matrix. And we call this matrix D. So basically putting attributes in columns and then agents, behavior, objects in rows. But yeah, I mean, probably not time to explain this in details. Similarly, we can imagine that certain roles can be described by the attributes. I mean, roles, they're abstract concepts, but eventually they will be a particular agent. So it's still attributes are still applicable. And the point with this matrix here that we get that describes the state of institution or of a context, it's reduced in size because there are less roles than agents generally, and attributes, and it uses only attributes that are used in norm semantics and not all attributes that describe domain, and they are smaller than, they have a small number than all the attributes. Okay, there are also two more. Okay, so we have domain matrix, but this domain matrix, it describes states only in time t. To make it describe the whole trajectory that we are interested in, we have to use a tensor, basically with a third dimension, which is time. Similarly, we can represent only relevant part of trajectory by creating a tensor from a T matrix, from a matrix that describes the context or the institution. Okay. So this T is basically the structure of the institution, and this represents a structure, and then semantics that's defined over this structure is its function. The thing is that this is stable, and if we change the domain, we can change physical domains, but we could still have the same institution. And the idea is that we want to learn from this matrix. So we have these stable inputs. And even if we change domains, to still use this matrix. And the question is how to basically interpret a state of a domain as a state of a context. And to answer to these questions could come from grounding and semantics, because I'll show you. So on the next slide. So first I defining this grounding matrix, and it simply says that, for example, role 1 is grounded to agent 2, as in the picture. Role 1 is grounded to agent 2, role 2 to agent 1 here. Yes, and the white part is all that we need to know. The other parts can be constructed automatically. There is another matrix which is called semantor indicator matrix, and it's only lists the attributes here that are used in our semantics. Basically, only relevant attributes, attributes relevant for the context of execution or institution. Here are all the attributes, and then basically, if you didn't follow this, doesn't matter. Imagine the domain matrix can be, the domain can be represented as this, the trajectory in domain can be represented as this tensor institution. There is also a matrix that captures the state of the institution. There is grounding matrix and semantic indicator matrix. And there is a relation between these matrices that is given by this equation here. So basically we have the D matrix, and then multiplying G from this side and S from this side, it leaves us only with T matrix, because what G does, it's removing it's removing unnecessary rows and leaves only rows that are describing roles and that are describing social actions and social artifacts. So all the entities that have something to do with institution. Similarly, this semantic indicator matrix, it removes the columns that are not important, and columns are the attributes. So if the attributes is not important for this institution context, for example, it's removed, and we leave only with T. And now we can start turn T into the vector and start learning with T. And we call this abstract learning. Basically, this leads to creation of these abstract policies that are learning on a higher level of abstraction. So not on a domain, but after interpretation of the context here. There's another way. This is just another way to look at the same thing. So there's this expression mind eyes, where robot can see a full domain and then interpret only what's important for the situation. And here how the whole schema looks like. So here is the physical domain. It's a representation of states here, and they are, depending on grounding and semantics, they are basically here in the this abstracted view. And from this matrix, we are basically learning. So we are learning on a higher level of abstraction. That's the thing. So yeah. So going back here, I'll show how experiment works. Basically, so yeah, the goal is for a robot to take this thing and also follow the norms. Okay, maybe into video. So here the Rob is searching for a battery because battery is grounded by goods, and Robbie wants to buy a goods. He is paying at cash register, and also there is this temporal norm that are saying that first take the battery and then come here and pay. And I try standard learning as a baseline for evaluation, and standard learning means that I didn't use matrix T, but I just use the state from the environment and create a vector. So basically no abstraction here. So it uses all the state that it gets, how usually reinforcement learning algorithms learns. Here, abstract learning is abstracting these states and then learn. In both cases, there is a feedback coming from fulfilling of the norms in this experiment. But because this is an abstract policy, then we are able to use this policy and online and change grounding to goods. For example, goods are grounded to drill now. So we are changing this grounding dynamically, and robots should start and go for the drill. Okay, we can change, we can say the goods is X, and it will go for the X. Okay, so this is not retrained policy. This is the same policy that was trained before. And also we can, I think it's in this video or no, not. Okay. Also, we can use the same policy without retraining by interpreting this new domain as something already known, which is a store institution. Here, for example, a robot is searching for goods, which is garbage bin. It will come here. Even if this is a factory settings, it's interpreting it in as a store basically. So it comes here, and instead of picking it up, it uses another action lift because it's grounded to getting goods, and yeah, and it's instead of paying, it's leaving, basically disposing of this item. And this is kind of a transfer learning when we use the previous learn policy in a completely new domain, because this domain can be interpreted as something learned before. Okay, so interesting thing also, I guess I'm running out of time. So the final thing is we can also use this to learn in multi-agent settings, because after all, these institutions and the whole thing is for multi-agent systems. And here there are two agents. One is grounded to a role of a seller, and it has only one norm, and that is to stay near the cash register. And Robbie has the same norm, same norms as a buyer. Plus one norm more to when it buys and when it pays to go out. Basically, it's interesting here that the seller and buyer they are interpreting differently the same environment, and yes, and it works. Like, and it couldn't work in a normal settings. In without abstraction. Okay. So a quick summary is what I represent here is a formal framework for institution which bridges the abstract representation and physical execution. We use norms to guide reinforcement learning agents so they can learn normative behavior. And this works, and it's also more efficient learning because we can abstract this state, which is basically okay. And then, yeah, and then this leads to transfer of learning, and it basically only start addressing this thing. There are implications of this, but I won't be discussing them now. And basically, thank you.
Well, thank you very much for this seminar, and it was really interesting. Talking about the AI and robots, how did you start this track? How did you come into this world of robot and AI?
Yes, so after finishing my cognitive science, I was very interested to continue doing research. And I came from the game industry when I did work a lot with software agents, basically that's NPCs in games. And I don't know, I liked robots in general, basically from, I don't know, from my childhood. But I didn't especially search that it has to be research with robots. It's just that I found this place and everything seems interesting, and that's it.
Yeah. How do you see, like, I mean, when we talk about normally nowadays in the role of development, working with customer products, such as in Synteda and also Semantics, how do you see application-wise? I mean, taking this research into the application, more realizing it. Do you see any difficulties with that, or do you see it's possible to just put it in?
Yeah, that's the interesting question. I think it should be pretty easy to put it in, but maybe there will be something that will need a little bit of research.
Yeah.
That's, I don't know if we should, because maybe we should discuss this in private, how it could be used for HiveMind, but in general, for example, I was thinking of application in game industry where you can train NPCs, basically these artificial agents, and then use them in different domains, different levels, or even different games, like
Exactly.
making this general agent. Or
yeah.
There are other applications that I didn't present all here because of the time and other stuff, but
yes,
there's this hierarchical reinforcement learning, and the current problem with this that it's using the policies that are concrete
yes,
on all its levels. So basically, it's possible to define this hierarchical learning where on all levels the policies are reusable, and that's something very interesting.
yes.
Okay.
Yeah, I strongly believe that, because this is an area that is becoming really popular. So I thank you again, Stefan, for being with us and holding this seminar. Yeah, that's all from Synteda and from us. Thank you very much. Take care. Bye-bye.
Bye. Thanks.